Okay, so in this question, we need to determine the types of intermolecular forces. And we are given three different molecules. The first one, bromine, fluorine. We're going to go ahead and draw out the Lewis structure for each one of these, actually. You have bromine bonded to fluorine. And since both of these elements are group 7, we need to make sure that there are 7 valence electrons. So we're going to add our lone pairs. And we also need to make sure that they are following the octet rule, especially fluorine. Bromine from time to time can break the octet rule, but we don't need to worry about that right now. So you'll notice that we do indeed have 7 valence electrons, 2, 4, 6, 7, 2, 4, 6, 7. And when looking at the octet rule, they each have 8, 2, 4, 6, 8. You consider the covalent bond as 2 for each element since they are sharing it. So for this one, the intermolecular forces that we have are immediately you're going to know you have dispersion. Everything has dispersion. All molecules have dispersion force. But you need to look at their electronegativity. Obviously, this is going to have some type of dipole since they're not the same element. Fluorine is the most electronegative element there is, period. So we know that you're going to have a little more positive side, the bromine, and electrons are going to be pulled towards the fluorine. So we can also say that we have a dipole-dipole force. And that's it for that molecule. The next one, methane. Go ahead and draw out the Lewis structure. There is our methane. We know we have dispersion. And it's very symmetrical. I mean, this thing is being pulled in every direction the same. So for methane, all you have is dispersion. Now sulfur dioxide, when we draw its Lewis structure, this one is a little more tricky. And this isn't sulfate or anything, so there's no charge on it. This isn't a polyatomic ion. It's just sulfur dioxide. It's one of the more challenging Lewis structures. When you draw it, that was a little off, but it's okay. There's our 2 oxygens. And we also, sulfur is in group 6. Right now we only have 3 electrons connected to sulfur. We're going to add a lone pair to sulfur. That's what gives it the bent shape, is the lone pair up top. But now we still only have 5 valence electrons for sulfur. But that's okay because when we look at our oxygens, we know that when you have oxygen with 2 bonds, it has a net 0 charge. But oxygen with a single charge is a single bond is gonna end up having a charge. So our sulfur, we know, has a positive charge right now. Oxygen, being group 6, we need to have 6 valence electrons. Right now we have 2. And since oxygen is in row 2, of the periodic table, it has to follow the octet rule. So 2, 4, 6, 8. It's following the octet rule now, and we have 1, 2, 3, 4, 5, 6. This has a negative or a net zero charge. Now this oxygen atom only has one covalent bond, so we need to add 3 lone pairs to it. 2, 4, 6, 8. We're following the octet rule. Now, when assessing the charge, we notice that we actually have 7 electrons directly attached to this atom, which is one more than it's supposed to have. So this is going to have a negative charge. But that's okay because sulfur has a positive charge, so these two charges are going to cancel out and we're left with a neutral molecule. Now when looking at the intermolecular forces of this molecule, we know immediately it's not symmetrical. It's bent like water, so it's very polar, and we have a dipole force. There's no hydrogen bonds because remember, hydrogen bonds have to be attached to either fluorine. Well, actually, there's not even hydrogen, so don't have to worry about that. And the only other force we have then in that case is dispersion. And those are the intermolecular forces of each one of these molecules. Best of luck to you.